Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. So this video discusses distributed forces in preparation to the internal force systems and the construction of the shear and moment diagrams in beams. Level 31. The beam AB supports two concentrated loads and rests on soil that exerts a linearly distributed upward load as shown. So determine the values of WA and WB corresponding to equilibrium. So here is the given figure. For the solution, let's divide the upward loading into two triangles. And let's call the equivalent concentrated load on this upper triangle as FA. And it is aligned to the 24 kilonewton load. The only difference it is upward because 1/3 of 1.8 is zero point 0.6, so that's why it's aligned. Then for this bigger triangular load, the FB, and it is zero point 0.6 from B. So it is also zero point 0.6 from the 24 kilonewton load or from FA. So that zero point 0.6 plus zero point 0.6 is 1.2, which is 2/3 of 1.8. So FA is 1/2 of 1.8 times WA. So FA is 0.9 WA. FB is 1/2 of 1.8 times WB. So it is also zero point 0.9 of WB. Then summation moments about A equals 0, counterclockwise positive. FB, by the way, this is also 0.6, that one. So FB times 0.6, 0.9 WB times 0.6, then minus 30 times 0.9 equals 0. So this is 0.9 because the distance of B from A is 1.8 minus 0.6, so 1.2. Since this is already 0.3, so 1.2 minus 0.3 is zero point 0.9. So solving for WB, WB equals 50 kilonewton per meter. Having found WB, then we sum up forces vertical. FA 0.9 WA plus FB 0.9 of 50, or WB equals 24 plus 30. So 0.9 of WA plus 0.9 of quantity 50 equals 24 plus 30. So from there we can solve WA. The intensity of WA is 10 kilonewtons per meter. Level 32, determine the reactions at the supports of the beam which is acted on by the combinations of uniform and parabolic loading distributions. So here's the given figure. For the solution, let's divide the loadings into rectangular as shown and parabolic loadings. Then we will call the equivalent loading for this rectangular distribution as F1. Distance from either end is half of 5, so 2.5. Since this is already 1, so that's 1.5 meters, then 2.5 from B as shown. Then we have F2. For this parabolic loading, the intensity here is 4, 6 minus 2. So 1/4 of 3 is 0.75 from the right. So call the reactions here as RA upward, and AX is 0, so that's why AY is automatic RA. Then at B R sub B. So F1 is 5 meters by times 2 kilonewton per meter, so 10 kilonewtons. F2 is 1/3 of 3 times 4, where 4 is 6 minus 2. So 1/3 of 3 times 4 is 4 kilonewtons. Then summation moment about B equals 0. So RA times 4 minus F1 10 times 2.5 minus F2 4 times 0.75 equals 0. So RA can now be computed. It is equal to AY, and it is 7 kilonewtons. Likewise, summation of moments about A equals 0. So R sub B times 4 minus 10 times 1.5 minus F2, which is 4 times quantity 4 minus 0.75 or 3.25 equals 0. So R sub B is equal to 7.00 kilonewtons upward. So that's it for this problem. Level 33, the quarter circular cantilever beam is subjected to a uniform pressure on its upper surface as shown. The pressure is expressed in terms of the force P per unit length of circumferential arc. So determine the reactions on the beam at its support A in terms of the compression C sub A, shear V sub A, and bending moment M sub A. So here is the quarter circular cantilever beam, and it is subjected to this circular loading along the arc. So we use the horizontal and vertical projection in order to compute for the compression, shear, and bending moment. So let's call the vertical reaction at A as V sub A, the compression as C sub A, and the bending moment counterclockwise positive as M sub A. Then for the loading, we have to obtain the projection. Vertical projection would be P, and it is acting or projected along the vertical length, which is R. And we will call the force as later. So likewise for the horizontal projection of the loading P, and the length is R. So we call that F1, and the horizontal equivalent loading here as F2. By the way, this is R over 2, which is half of R, and that is F2, and the distance from the top is also R over 2 because the vertical distance is R. So summation forces horizontal, C sub A equals F2, and F2 is just PR. So F1 equals P times R, F2 is also P times R. So summation forces X equals 0, C sub A minus PR equals 0, so the compression at A is PR. Then likewise, summation forces vertical equals 0, V sub A minus F1 equals 0, and F1 is also PR, so V sub A is also PR upward. Then finally, summation moment about A counterclockwise positive, so MA minus PR times R over 2 minus F2, which is PR times R over 2 equals 0. So MA equals PR square, and it is counterclockwise as shown. Level 35, the intensity of the line loading acting on the rim of the semicircular plate varies as W equals WOY over A, where WO is a constant and A is the radius of this plate. Use integration to determine the resultant force and locate its line of action. So here is the figure. Then let's consider a sector element so that the strip would look as shown. So we have a vertical strip, triangular strip. The height is WO, the intensity of the load, and we have it is subtended. The thickness is subtended by differential angle d theta. The radius is A. The angle that the radius makes with the x-axis is theta, and the angle subtended by the width of this strip is d theta, so that the length of the strip along the arc is radius times d theta. So it is a d theta as shown, so that the differential force, which is the area of this differential element, is a d theta times W, or WA d theta. And this distance is y, which is equal to y sub c. And in terms of the radius or hypotenuse, it is a times sine of theta. So y equals y sub c, and it is a sine theta, as shown in the figure. So that's differential force. This is the force. By symmetry, the force acts on the y-axis, so xg is 0. And this is y sub g. So differential force is W times A d theta. Substitute dF equals W, it's WY over A times A d theta. Cancel out A. So dF is WO integral of y d theta, where y is A sine theta from the figure. So integral of y, which is A sine theta d theta. Since A is constant, so F is WA. Integral of sine theta is negative cosine theta from 0 to pi. So theta varies from 0, from the positive x-axis to the negative x-axis. So substitute F equals negative WA, quantity cosine of pi minus cosine of 0. Cosine of pi is negative 1 minus cosine 0, 1. So negative 2 times negative 2 WOA is positive 2 WOA. So that is F. Then apply Varignon's theorem. F times xg is yg is integral of y sub c df. So there's no need to derive xg because by symmetry it is 0. So substitute y sub c, by the way, is y, and it is a sine theta also. So 2WOA yg equals integral from 0 to pi of y, and WOY d theta. Substitute the value of, so we cancel WO, so 2AYG equals integral of y square, and y square is a sine theta, quantity square d theta. So by identity, sine square theta is 1 minus cosine 2 theta all over 2. So 2A yg equals a integral 0 to pi of 1 minus cosine 2 theta over 2 d theta. So 2yg equals a over 2 quantity theta minus sine 2 theta over 2 from 0 to pi. Remember that sine of 2 pi is 0 and sine of 0 is 0, so don't mind the second term, just the first term. So upper limit theta minus lower limit 0, so this is just pi. So yg is pi a over 4. A over 4 times pi minus sine of 2 pi over 2, which is 0, minus lower limit 0, so pi a over 4 yg. Then by symmetry, xg is 0. So that's all for this problem.